Yeah, piezoelectric sensor. Yeah, so this comes from two words basically, piezo. Yeah, which is okay. You can define it as pressure. Then electric, of course, is as electricity or electron current. Okay, and as the name implies, you may already guess how this how does this sensor work. Yeah, because its name resemble the piezoresistive sensor. Okay, what's then the difference with piezoresistive sensor? So in piezoelectric sensor, uh, the parameter, the energy or information is being converted between pressure and electricity, and electricity in pressure. Electricity here is voltage parameter. So this type of sensor uses the material piezoelectric material, the type of ceramic material. Usually they are ceramic, but there are also polymer, piezoelectric polymer. A piezoelectric material will convert any pressure change or pressure stimuli into voltage change. And vice versa also, when you apply voltage to a piezoelectric material, it will convert that potential difference between its two ends into force from coming a stress, yeah, that is done by that material, yeah, at both ends. And that is why piezoelectric sensor, the material itself, can also be used as actuator, piezoelectric actuator in some of high precision nanometer scale actuator. They use also piezoelectric material as actuator, as the transducer. Usually as a sensor, then it will detect the amount of force or stress being exerted onto its two ends, and this force will polarize. Yeah, because the piezoelectric material basically is a kind of dielectric material. Only it is sensitive towards pressure. So the charge will be polarized to both different ends, the positive charge at one end, negative charge at the other end, and they will create potential difference. Therefore, hence, then current or voltage can be measured from the two ends. Okay, and now you can see that they are widely applied in many different applications. Okay, so again, this stems from piezoelectric effect, piezoelectricity, and piezoelectric material. Yeah, the piezoelectric materials are based on piezoelectric effect, and this is uh, discovered by the Curie brothers, not Madame Curie, but the the, the husband of Madame Curie, one of them is Pierre Curie. I think it's the husband. Yeah. Pierre and his brother Jacques Curie. Well, they are investigating tourmaline and quartz, and these two materials behave as piezoelectric material. That is the ability to transform energy of a mechanical input into an electrical output. Okay, so in this case, the pressure or voltage that is exerted onto the material is converted into voltage. When a pressure, piezo, yeah, that's from the Greek word piezo, which means pressure, applied to that material, it causes a mechanical deformation. So here, mechanical deformation, and then displacement of charges. So not only it mechanically deforms, yeah, basically what you learn already in biomaterials, yeah, for many materials, metals, also ceramics, polymer. Also, when we apply stress, there will be strain. Yeah, there will be strain. So the relationship between the two is what we call as Young's modulus. Yeah, E equal to sigma, the stress divided by strain. The Young's modulus is the gradient. Yeah, sigma equals to epsilon E. The gradient in the sigma epsilon graph. When we apply strain, it's a graph like this. This gradient is the Young's modulus, and ceramics usually has very high Young's modulus. But in piezoelectric material, in addition to that mechanical deformation, it will also displace the charges within it. Those charges are highly proportional to the applied pressure, which is called the piezoelectric effect. And later there is a converse piezoelectric effect where, as I mentioned earlier, that when we apply voltage across the electrodes at the two ends of the piezoelectric material, it will induce mechanical deformation of the media. Okay. So here is the piezoelectric effect. We apply forces at the two ends of the piezoelectric material, and the charges will be displaced the two different ends of the material. Yeah, so here we create a positive charge in the one top end, negative charge at the bottom end, and as a result, when we connect it into a wire, current will flow due to this potential difference between the two ends. Put ampere meter here, and we will indicate that there is current flowing. A converse piezoelectric effect, the reverse one, is when we apply voltage difference between the two ends. Okay, then positive here, negative charges will go to the positive charge, and the holes will go to the negative charge here. And not only that, it will make the material to deform. Yeah. So this is quite interesting material effect actually. So from the Curie's initial discovery, the first application was used in 1950s. And therefore, this, as I mentioned, usually they are used as mechanical transducer or as a resonator. At many of the old computers, I'm not sure if today it is still used, but many of the old computers, they use quartz resonators that come from quartz. Remember, quartz is basically a silicon dioxide, yeah? One one form of silicon dioxide. Yeah? It can also have other form. And this is piezoelectric. So when they use it as a resonator, they apply AC voltage with certain frequency. So then the polarity will change, right, between the two ends of the piezoelectric material. So as a result, the resonator, the piezoelectric material will expand and contract, vibrating uh, the same at the same frequency as the uh, incoming the frequency of the voltage. Okay, so they are used as mechanical transducer as well as resonator, where the observed resonance frequency and amplitude are determined by the physical dimension properties and materials comprising the device, and most importantly by the mechanical and interfacial input of to the device. Okay, so let's see this here. There are two modes of operation of piezoelectric sensor. The first one is as direct piezoelectric effect, where the change, any mechanical stimuli change that we apply to the material is converted into voltage change or charge change or frequency or dissipation change. We could also use it as a mechanical transducer. So we don't just passively measure the uh, voltage that coming from the two ends, but we put voltage first to vibrate the piezoelectric material um, to generate acoustical wave, yeah, and then any change to the medium where this acoustic wave traverse, okay, or flows or propagate. If there is any change in the medium, then it will change also the property of that acoustical wave. So this is a kind of positive, a kind of active sensor as well, this acoustical wave propagation, because energy is being inserted into the piezoelectric material to vibrate it so that it can emit acoustical wave. Acoustical wave means this mechanical wave, a physical wave that transfers inside the medium itself, inside the mechanical physical medium, not through the space. Okay. So when something happened to the mechanical medium, like when you put force or chemically it change, etc., or the surface property change, then the acoustical wave will the acoustical wave propagation will also change. Usually, in terms of the velocity, the wave propagation velocity will also change. Then we can detect, we can relate this to the stimuli. In direct piezoelectric effect, uh, we operate the material more of as direct stimuli, force stimuli to voltage chain converter or transducer. Okay? So anything that can change the property of that material, of the piezoelectric material, either at the bulk condition or at the surface of the material, will change the piezoelectric property. So in one or another way. So that means that the voltage will change, yeah, or the charge will change. So usually many of them are many of them belong to mechanical domains, parameter like acceleration, angular rate, pressure, as of course we have just given the example. Force also you apply force. Also mass, yeah, mass change on top of it, either at the surface or the bulk itself. The bulk property, the mass change, for example, when it absorbs chemicals. The viscoelasticity property of the piezoelectric material, or temperature also. When temperature change, the property of the piezoelectricity will also change. Due to magnetism also. Why magnetism? Because magnetism can attract also the charge. The charge will not be can be attracted at different field. The electron. Yeah. So in that case, the, the property will also change. Yeah. Or biochemical. So many of the quartz or piezoelectric material are used also as secondary transducer for biosensor, where they put an antibody or antigen or DNA probe on the surface of the piezoelectric material. So upon binding to the complementary molecule, and then the mass will change. The mass or the surface of the piezoelectric material will change. So you could detect it. Usually this is in the acoustical wave propagation mode rather than direct piezoelectric mode. Okay, so there's this input signal goes into the piezoelectric element. Either you use the direct piezoelectric effect or acoustical wave propagation to give change to the sensor output. Yeah, and usually it direct is more of voltage. If acoustical wave, usually frequency change. Otherwise, you can also detect the charge accumulated on the two electrodes of the piezoelectric material, or as dissipation of energy. So there are two groups of material used for piezoelectric sensor: the piezoelectric crystals and the piezoelectric ceramic. Okay. And we will introduce the piezoelectric equation here. What is the material that converts the stimuli, the mechanical stimuli, into electrical field, and the vice versa also, the electrical field into mechanical stimuli. For example, here then in equation 3.8, this equation, you see that Sj here is the mechanical strain, then sigma j here is the mechanical stress. So this is, here is if from strain converted into voltage or into electrical field. So di here is the electrical displacement, and then Ci J is the elastic stiffness constant. This one, yeah. And Sij small, S small ij is the elastic compliance coefficient. This one, compliance is basically the inverse of rigidity or Young's modulus. Epsilon ii is the permittivity. Okay, and then if a parameter has a superscript like this, as like this one, this is the elastic compliance when the electric field is held constant. So the piezoelectric coefficient is this small d and small e, dij and eij, that are third rank tensor. Tensor is an extension of the vector concept, yeah, it's in the form of matrix. Because here it means that they could, this property may be different in different crystal direction in the XYZ direction. Yeah, the indexes 1, 2, and 3, the I, they will define a normal electric field or displacement orientation. J, here 1, 2, 3, define the normal mechanical stress or strain. And J 4, 5, 6 represent the shear strain or stress, because so for it the response can come from both axial mechanical stress or strain and as well as from shear mechanical stress and strain. So remember the class in biomaterials, yeah, about the difference between these two. So these two equations describe the basic relationship of direct and converse piezoelectricity. So this uh, describe the what is the this one describe the piezoelectricity effect. Okay, although D here is the small d is uh, piezoelectric coefficient. If this is if you use stress, if you use strain, this is multiplied to small e, and this is the permittivity multiplied to the electric field there. The converse piezoelectric effect is in this equation 3.9. So from strain or the inverse of this, yeah. Indirect effect equation 3.8, yeah, a mechanical stress sigma or strain, yeah, sigma j or strain sj will cause a net electric displacement di. That's why then the charge move to both ends of the material with different charges, yeah, positive at one direction, negative to the other direction. The magnitude of which, yeah, on the I phase of the material, the magnitude of which depends on dij and eij respectively. The converse effect is expressed by equation 3.9. Yeah. Relates the induced normal and shear stress. Here S normal shear strain and stress to the applied electric field via the piezoelectric coefficient tensor. Swatch. This is the reference. Large piezoelectric coefficient D, the small d, with the unit is picocoulomb per Newton, yeah, because it converts the force into charge separation, yeah, like a dielectric material, like in capacitor, are desired in actuator application. Large E coefficient are desired for sensor application. Okay, okay, now let's look at some of the types of piezoelectric materials that are used as piezoelectric sensor. So quartz, yeah, I've mentioned that quartz is silicon dioxide. Basically, it could be like here, crystalline, yeah, 80 cut single crystal. This is what is also normal used in computer, I think. Quartz has a trigonal structure, and beyond that temperature of 570 degree, it becomes beta quartz with hexagonal structure. Okay, and quartz is only useful in single crystalline form. So usually it is in the monocrystalline form to achieve high resonance frequency. For a computer application, usually that's why they could be as high as in megahertz or gigahertz. The thickness of this crystal quartz must be minimized. When it is very thin, the frequency can be made very high. Using micromachining techniques, the resonators with less than 10 micrometer thickness, diameter of less than 100 micrometer have been realized for QCM, quartz crystal microbalance now. So remember, yeah, this we will be encountering these words multiple times. So basically, QCM is a balance, yeah, or a balance or analytical balance. It measures mass. It is very sensitive to mass change. Okay, so it is operated by applying AC signal into it with certain frequency, which will make this QCM to vibrate and or resonate, yeah, at certain resonance frequency. When it absorbs certain chemicals, or which makes the mass change, the mass of that QCM changes, then the frequency will also change. The resonance frequency will change. Okay? And that is why it is usually used a lot in chemical sensing application, where, for example, and the antibody is being deposited on top of the QCM. So if you have like this, you can deposit, we call it immobilize the antibody. So when then, so here, even when upon immobilization, the frequency will change. So if this is frequency and this is, let's say, arbitrary unit, yeah, for example, before antibody immobilization, it is like this. When there is added antibody, yeah, the mass will increase. So if the mass increases, the frequency will be, wait, shift to the right or to the left, higher frequency or less frequency. I think uh, less frequency, yeah, smaller frequency. So it will be shifted to smaller frequency. Yes. So this is the what you call as the natural resonant frequency, Fn. And this, when after it is shifted, and it become Fn dash, for example. Later on, when you flow, for example, in a device, the antibody, the antigen that can bind to this antibody like this, yeah, this frequency will shift to even lower frequency, right? Like this. Uh, so in application of chemical sensor, then usually we measure here delta F as a function of this mass change on the surface of the QCM. It could be very sensitive. Depending on the design of the QCM, we can make a very sensitive chemical sensor. Okay. Then another type of material, langasite. Langasite, which has similar temperature coefficient as quartz, that has quality factor 5 times higher. What does it mean with quality factor here? So quality factor is how sharp the frequency, the resonance frequency will look like. So earlier I draw, right, like this. If it has a higher quality factor, yeah, then the frequency peak here will look even sharper. Yeah. So for example, like this. Uh, okay, so the black one has higher quality factor compared to the red one, and this is also a property that depends on the crystal state of that material. Now, in langasite, it has 5 times higher quality factor compared to quartz. Okay. So it is grown using Czochralski method. So I will not go too deep into this method. Yeah, this is a special method in crystal growth. Crystal growing. Remember about nucleation and crystal growth in biomaterial? Yeah, this is one of the method to develop single crystal of thin films. Yeah, to grow single crystal thin film. Okay. Then lithium niobate and tantalite. This is also quite a famous piezoelectric material. Okay. This one is the formula for lithium niobate, and this one is lithium tantalate. This one lithium tantalate. They are well known ferroelectric crystal, successfully grown into single crystal, and the material must be grown in bulk. It cannot be in the form of thin film, and different properties will have different properties based on the cuts. They usually are cut as Y cut. It's oh sorry. Then another famous piezoelectric ceramic material is this PZT, lead zirconate titanate. Yeah, lead zirconate titanate, or if we write the chemical formula is something like this: lead zirconate titanate. I hope if I'm not mistaken, this will be like this. Please check later. Yeah, lead zirconate titanate (PZT). So this is quite widely used ferroelectric material. The and it has very high electromechanical coefficient. So because it means the piezoelectric coefficient is high with a certain force, it resulting voltage, converted voltage can be very high, or vice versa also. With small voltage, you can make a high extension, a big extension of the material. That's why EZT is very often used also as actuator, especially in MEMS device application. What is MEMS? MEMS stands for micro electro mechanical system. So a device that combine electronic and mechanical system at very small scale, at micro scale level. Then we have other type of ferroelectrics. Ferroelectrics is basically the general classes of piezoelectric material. We have lead tectonic relaxation based ferroelectric system (PZN), lead zirconate, and with PT, lead titanate, PMMPT, PYNPT, yeah, and so it can be combined even to make a ternary system of different composition, like a mixture of PZN, yeah, with PET, yeah, and with lead, with B1 and B2, yeah, stands for some elements. Then piezoelectric can also be polymer. And this is one of the famous polymer that has characteristic as piezoelectric material. Polyphenylidene fluoride (PVDF). Yeah, the monomer is CH2CF2 here. Okay. A semi-crystalline homopolymer. So when it forms a large chain, it can make a crystalline structure. And it is very important technologically because it has piezoelectric property as well as pyroelectric properties. So pyro means that it can transform temperature increase into voltage and vice versa, voltage into temperature increase. So these characteristics are useful in sensor and battery application. And in addition to that, compared to the ceramics-based piezoelectric sensor, PVDF is also flexible, has flexibility, quite good stability over time, does not depolarize when subjected to very high AC, alternating electric field. Okay. However, it has smaller piezoelectric coefficient. It's a drawback of this PVDF. So if only that the piezoelectric properties are increased, are enhanced, then the application can be even more, yeah, because of it is flexible material, it may be easy to process as well compared to ceramics. Then how do we process the signal coming out from piezoelectric sensor? So piezoelectric sensor can be modeled usually as a charge source with a shunt capacitor CT and resistor RT as a voltage source. It has also usually high inner resistance and low output energy. That is why we need to use preamplifier circuit with high impedance. Yeah, so we only convert the voltage. So this is typical one of the two example of circuit. The first one is voltage amplifier circuit here. So the piezoelectric material here is modeled as a charge source. A QT here is charge source in parallel with a capacitance, and resistance, yeah, internal capacitance and internal shunt capacitor and shunt resistor. This, yeah, the voltage of which we can measure using this voltage amplifier. The formula of the V out here will equals to GT here divided by CT plus CP multiplied by RF times R1, and this is an inverting amplifier. Yeah, so there is a minus sign here. The circuit is a charge amplifier circuit. This one is voltage amplifier. This one is charge amplifier. So we put the feedback arm. We put not only resistor, but we put also shunt capacitor CF. So in this case, then the V output will be equals to negative QT divided by CV. So the V out is proportional to the charge value. Let's see some biomedical application of piezoelectric sensor. Some sensor based on direct piezoelectric effect. Yeah, for example, monitoring breathing condition during sleeping. Yeah, so where, for example, this can be like this. This piezoelectric film, yeah, is deposited on top of a metallic substrate. When there is a force at the end of this cantilever, so this is what we call as cantilever structure. A cantilever structure is a beam where one end is fixed and the other end is hanging. So this can deflect. It can be deflected up and down. Okay, so here, for example, the substrate material consists of stainless steel. Then the piezoelectric film is made from PZT composite. Okay, so here you can, for example, detect, if you put it in near the breathing system, you can detect, for example, snoring, for example, yeah, breathing condition during sleeping. Yeah. Then QCM. Yeah, we have discussed about a little bit about QCM. Yeah? So a QCM typically consists of slab of tin or single crystal or piezoelectric quartz with very large lateral dimension. It looks like this. So we apply the voltage here at the bottom as well as at the top. Here, this layer. Okay. And there's a polymer film here covering it. We can deposit or immobilize any biomolecules on top of it, which will adjust or will modify its natural frequency, resonance frequency. Okay. So with an alternating current between the electrodes of NDT cut crystal, we will have a standing shear wave, acoustical wave. Yeah. The resonance is narrow, so that oscillators are highly stable and accurate in determination of the resonance frequency. So again, when we use piezoelectric material, this one is in the acoustic wave mode. We detect the frequency shift, the resonance frequency shift due to the mass that adsorbed on the surface of this QCM. Yeah, the delta F, the frequency shift, equals to, can we model like this equation, minus N is, I think, the number of molecules, times delta F, in N mode of the delta Fn here of the frequency. Delta Fn is change of the oscillation frequency of quartz crystal on the N mode. Delta M is the mass change of the crystal electrodes, yeah, due to the absorption of chemicals, for example, due to humidity and many others. The fundamental frequency here is represented by F1. A is the electrode, the area of the quartz. Mu is the elastic modulus of the quartz, and rho is the quartz density. Okay. The equation is examined experimentally by measuring the change in oscillation frequency when the deposit mass of polymer films affected the oscillating frequency of the QCM. Okay, and later, after, when the polymer film is also sensitive towards other chemicals, yeah, for example, like volatile organic compound, methanol, ethanol, whatever, it will also create frequency shift change. This is also the principle of electronic nose, e-nose. Yes, not only based on that. There are also other electronic nose that is based on silicon semiconductor oxide resistant based gas sensor. Yeah, but some of the electronic nose are based on QCM uh, mechanism. So they have an array of QCM, like QCM quartz crystal microbalance. They put different polymer film. So it means then each of these element that will have different polymer film, yeah, can be sensitive towards different types of chemicals of gases. Okay, so then when it absorb, then the frequency resonance frequency will change differently depending on the gas composition. QCM can be used in gas phase, but also in liquid environment. It's useful for monitoring the rate of deposition in thin film deposition system under vacuum. In liquid, it can be used to determine the affinity of molecules, as I mentioned, yeah, in biosensor application, to surfaces functionalized with recognition science. Okay, then as resonator also we can use it. We can uh, use electric resonator as infrared detectors. Yeah, well, one of your projects is about infrared, but this is with different mechanism, not using resistance-based change due to the infrared radiation, but instead it is being resonating. So when like this, and it is coated with material that can absorb infrared. So when this material absorb infrared with certain wavelength, the temperature increase will change the resonance frequency. For example, this one is 7.2 kilohertz per degree Celsius sensitivity to temperature change. Yeah. The resonance frequency F is that is 89.65. This one in figure. So based on that change, due to the different temperature change at each of the pixel, then we can reconstruct an infrared image based on that. Yeah, like this. Yeah, here, and then it formed an image. So like night vision, or if you like to see many movies, yeah, especially war-related movies, yeah, then you will see some like this term, what you call as thermal image, and this is also can be used for diagnostic as well. Yeah, also for thermal imaging camera in the airport. Although not all of them use this piezoelectric resonator principle. Some of them use different principle. Yeah, here they use different ferroelectric bottom and top, and then also a mirror to reflect the incoming infrared so that it can go back to heat up the ferroelectric metal. Okay, I think that will be all for